on. As far as I know, everything you've ever been taught about graphing points has been on the rectangular coordinate system. It's the x and the y axis, right? We graph everything on the x and the y axis. Points on the rectangular coordinate system are labeled as x, y. This is also sometimes called the Cartesian plane. So if you see that phrase, Cartesian plane, that is the regular old XY coordinates, rectangular coordinate system. Okay. The idea with rectangular coordinate system is that if I want to get somewhere, if I'm on a graph, right, then I'm going to use my X and my Y coordinates, and I can only go left or right or up or down, pretty much, right? So if you know, like, if I'm at the origin, and I want to get to the door, right, then I can't go straight to the door. I have to go to the right this far, and then up this far. And the cabinets are a little bit away. I'm not quite to the door, but I'm about there, right? So I can only go up, right, up, down, left, or right. Okay, that's the idea for the coordinate plane. But let's pretend the desks weren't here. If I was standing right here and I wanted to walk to the door, let's pretend the desks aren't here, we won't move everything, but if I want to walk to the door and nothing's in my way, I just go straight to the door, right? If you think about being in like a standard position, I turn towards the door and then I walk straight there. That's sort of how polar coordinates work. You turn in the direction that you want to go with an angle, and then you go a certain distance in that direction. So it is very helpful whenever you don't have anything in the way, right? If the desks aren't there, it would be silly if I, walked like I was in the military doing sharp turns to get to the door, right? But whenever I teach this, I think of the scene in Shrek whenever he just goes like straight through all of the ropes that are there. That's the polar coordinates right there. He's not going to go along the path he's got to go through. It's straight directly there, right? In the polar coordinate system, it uses an angle and radius to locate each point, and points are labeled as r theta, where, of course, that r is radius, and theta is your angle. Oh, I've got that here. Absolute value of r is your radius. I should put it here. I was not paying attention. And theta is your angle. So, if you look at this graph that we have here, it looks like a unit circle, kind of, right? The unit circle is on this graph, but the unit circle has a radius of 1. So the unit circle would be like right here. Right here. There's the unit circle. It's on this graph. So what you're seeing right here, on this axis right here, this is your radius. And then you can see your angles work like the unit circle. So if I want to graph the point 2 pi over 3, I'm going to really start with my angle, right? So pi over 3, just think about the unit circle. Where's pi over 3? It's right here. There's pi over 3. Okay? And so you're going to begin at the origin. The origin is actually not called the origin on a polar graph. It's called the pole there. But we can think of it sort of as 0, 0. And I'm going to go not up, down, left, right. I'm going to go out with a radius of, here's a radius of 1, and here's a radius of 2, and I put my dot right here. There's point A. Okay, so you find your angle, that tells you which direction you're going in, and then you go out however far your radius is. So if I wanted, let me use a different color for B. Right here, if I want 3 pi over 2 to be my angle, 3 pi over 2 on the unit circle is right here. and I want a radius of 1. So I'm going to always start right there at the pole, right there in the middle. And then you're going to go out towards 3 pi over 2, but just a radius of 1. And you can see all those other like smaller circles inside. Those are for if you only want to go part of the way, right? So if you have like 0.5, you would go just halfway here, right? You have to be careful with polar graph paper, like whenever you see polar graphs, because sometimes it's like a little different how they like mark things out. So let's do a different color here. Let's do red for C. I've got 4 pi over 3. 4 pi over 3 is right, careful with this. 4 pi over 3 is right here. I almost went to this line right here. When you're thinking of the unit circle and how it relates to this graph, right here, here is pi over 6, here is pi over 4, here is pi over 3. You know, you're using these 3 right here. Polar graph paper is going to have these little extra lines that are not on the unit circle. Now, whenever I give you like a blank unit circle, they're sort of those aren't evenly spaced out, right? So this would be like 15 degrees right here, or pi over 12. So everything's evenly spaced out on polar graph paper. So there are some pieces that are not on the unit circle. So 4 pi over 3 is right here. I need to go out 1, 2, 3 circles here, 3 of the big circles. So right here would be point C. Point D, let's use a different color, got a blue. For point D, I've got negative pi over 6. Negative pi over 6 means I go in the negative direction pi over 6. So it's right here. It's the same as 11 pi over 6. They're in the same position. And I need to go out 1, 2. So this point right here would be point D. Let me use a different color than blue. It's fading in with that. You can. And we'll talk about that here in a second, because it's a little crazy. Okay, I think these also look a little bit like if you ever see like radar on the screen, looks a little radar. That's sort of what radar is doing, right? Radar bounces off a signal, goes back at saying, hey, there's something in this direction and it's this far away, right? Whenever, several years ago we went on vacation down to, I think it was Charleston, and they got the big battleship there. Any of y'all been to the big battleship at Charleston? And when they let you go in like the, like captain's navigation area, there's big charts that look just like this. There, I took pictures of them. I need to, but it was like on my old phone, and it's not. I need to go find those pictures because I was excited about that whenever I saw those giant polar graphs, basically, that were there for those. So try the next ones for example 2. But D's going to be weird because that's what Evan's kind of asking about here, a negative radius. You might not want to try that one yet. The other 3, you can try. Something weird happening. try these, something weird should be happening. What's happening here? They're all in the same place, right? Let's look at it here. And part D, you probably don't know they're all in the same place, but they are there. So let's look at it here for this. So pi over 4, 2. Were you guys all good getting A in the right spot here? Pi over 4, you go out 2 circles. So negative 7 pi over 4 is not like on our unit circle, right? But I could do negative 7 pi over 4 plus 2 pi to get it to be a value that is on the unit circle, which is negative 7 pi over 4 plus 8 over 4. And that is pi over 4. You're going in the negative direction, 7 pi over 4. You end up in the same spot, right? Same radius. 9 pi over 4. Again, not on the unit circle. It's too big, right? But if I do 9 pi over 4 minus 2 pi, that is 9 pi over 4 minus 8 pi over 4. And I get pi over 4 there as well. So all three of those are in the same spot, right? Does that make sense? Those angles are all the same. 5 pi over 4. Now, this is the one we haven't seen yet. 5 pi over 4 is not in the same spot. Okay? 5 pi over 4 is right here. Well, I don't want to put a dot like it's a dot. 5 pi over 4 is right here. Now, I'm going to highlight that line at 5 pi over 4. And I'm going to go all the way across here. 5 pi over 4 and pi over 4 are opposite to each other on that unit circle, right? So when you have a negative radius, you go away from pi over 4, right? So instead of going to pi over 4, which would end up here, this would be the point positive 2 5 pi over 4. You go away from 5 pi over 4. So you would go 1, 2 away from 5 pi over 4. You also end up at that same spot again. So this is very different than the rectangular coordinates, right? Because if you have the point 2, 1 on the regular rectangular graph, 2, 1 is the only way you can identify that point, right? If you make it 1, 2, it's not the same anymore. And if you change anything about it, it's not the same point, right? So in rectangular coordinates, there's only one way to talk about a single point. But in polar coordinates, there's technically infinite ways to talk about this same point right here. Which makes the graphs really cool. Like when we start doing equations, today we're just doing points. We're not going to go past points today. Okay, so example 3 says for us to plot the point with polar coordinates. So I want you guys to do that for me. I'm going to freeze my screen so you can't see it. Plot that 3, 5 pi over 6. Okay, check with your neighbor, see if it's in the right spot. See if they got it in the right spot there. Okay, here's what I've got. Double check your neighbors. It needs to be on the outer ring because that has a radius of 3. Make sure they didn't put it right here, like right next to the polar axis right there. It's got to be sort of like 2 angles up. Make sure they've got it. We're good here? Okay, so we've got to write it in 2 different ways. Okay? So you have two options. You can use different angles, or you can use a negative radius, right? Negative radius, I kind of like those. I think they're kind of the easier ones to do. If you go all the way across over here, draw a straight line, right? Then 5 pi over 6 is opposite 11 pi over 6. They're on opposite sides of each other, right? So if I use an angle of 11 pi over 6, but I use a negative 3 right here, then that means that I find 11 pi over 6 and start right here at the pole, but instead of going towards 11 pi over 6, I go away from 11 pi over 6 with a radius of 3, and I would end up at that same spot. Okay, so that's one way you can use negative radius, right? Can somebody give me a way to do this with a different angle besides 5 pi over 6 or 11 pi over 6? Okay, so 5 pi over 6, that's this direction, right? But if I went this direction, negative 7 pi over 6, I'd be in the same spot. So I could do 3 negative 7 pi over 6. Now, these are not your only options. There's so many variations of this. What's another way I could talk about 11 pi over 6? Negative pi over 6. So this angle is the same as negative pi over 6. So I could do negative 3 negative pi over 6. I don't know why I'd want to do that, but I could, right? That'd be in the same spot. Maybe instead of using a negative angle, I could do 5 pi over 6 plus 2 pi, right? We can always add 2 pi as many times as we want, and we get back to the same spot. So if I did that, I'd have to get common denominators. I'd get 5 pi over 6 plus 12 pi over 6, and that would give me 17 pi over 6. So I could use 3 17 pi over 6. All of these would be in the same spot as 3 5 pi over 6. Now, it only asked for 2, but I put a few extra just to show that those were not the only 2. And we could keep going with this, right? We could keep going forever. I need to do a little more exploration with Desmos, but I am pretty sure that if we graph like 3 5 pi over 6, it does not graph the polar coordinate there. It is going to graph the point 3 2.617. Okay. So, at least in its... You can put the circular graph there, but is this the point 3 5 pi over 6, the one we just graphed? No. So, if you just type in a point, it is going to graph it in rectangular mode. Okay? And I know it'll graph polar equations, but I don't think it will graph just polar coordinates. I need to look into that more because I think I remember James Steele telling me last year that it really would, because he was always telling me something Desmos would do that I didn't realize. But I never did look into that more, and I'm pretty sure it's more complicated than it is going to help anyway, like what you got to do to get it to graph. If you graph this, it's not going to graph polar coordinates. But the thing is that if I graph like the point 2 3, and I go over here, I can change my background, and the point 2 3, I could give 2 3 polar coordinates, right? So it looks like it is an angle of almost pi over 3, so it'll be a little less than pi over 3, right? And it has a radius of probably about 2.5 or 7 there somewhere. No, 3.6 or 7 there for that. So polar coordinates and rectangular coordinates are like interchangeable. It's almost just like the background is changing. So that is essentially what this is doing here. Like if I graph y equals 2x minus 3, that is the line that we know, y equals 2x minus 3, right? If I click over here, all it does is change what the background of it looks like. So we can talk about things either in rectangular mode or in polar mode, and it can be the same line or the same point that we're talking about. So that means that rectangular coordinates and polar coordinates can be converted to give you the other, right? So if you have polar coordinates, you can convert that to rectangular coordinates, or vice versa. So let's think about how it works. Okay, so in rectangular coordinates, what I do when I'm graphing, if I want to graph the point x, y, I start at 0, 0. I go over x, and I go up y. That's how I do it, right? But if I am graphing in polar coordinates, I find my angle, which is my direction, and then I start at the pole, and I go out however many the radius is. Now, these two pictures right here can be put together, right? Right here is my angle. Right here is my radius. There's the polar part of it. And then my rectangular is I go over x, I go up y. So if I look at this graph right here, cosine of theta is what? Cosine is which one over which one? Opposite, adjacent, hypotenuse, which one is it? No, opposite over adjacent is tangent. Adjacent over hypotenuse. So cosine of theta is adjacent over hypotenuse. So Asher, if I'm looking at this graph, what is the adjacent side? Good. And what is the hypotenuse for that? Nope. R. There. So cosine of theta equals x over r. I also could just like multiply both sides by r if I want. So x equals r cosine theta. Have we seen that before? We have. We wrote that down. That was our x coordinate whenever we had a circle that had a radius that was not 1, right? So like on the unit circle, x equals cosine theta. But on any circle bigger than 1, x equals r cosine theta, right? So we've seen this before. Sine is going to be similar. For sine, you're going to have y over r, and sine of theta is opposite over hypotenuse. So y over r. So if I multiply both sides by r, then y equals r sine theta. So we've done that before, just we weren't talking about polar coordinates whenever we did it, right? But it can be used to convert from polar to rectangular, okay? So, for example, here, I've got to convert the following points from polar coordinates to rectangular coordinates. So these are polar coordinates. That means my r is 2 and my theta is pi. So if I want to know the x coordinate, I just need to do r, which is 2, cosine of theta, which is pi. Okay, how do I find cosine of pi? It's going to be on the unit circle. Pi is right here. -1, 0. Cosine is your x coordinate. So cosine of pi is -1. So my x coordinate is -2. And y is going to be 2 sine pi, which is 2 times sine of pi is 0, so we get 0. So your x coordinate is -2, your y coordinate is 0. Okay, this is your answer. Those are your rectangular coordinates. So I'm going to flip over to Desmos. Watch this. If I graph the point, I said Desmos won't really graph polar coordinates, but it will graph rectangular coordinates. There's the point, 2, 0. Everybody see it? Let me make it a little darker. Right there. 2, 0. Watch what happens if I change my background here. Oh, it would help if I graphed the right point. What have I done wrong? It's -2, 0. The little tab right there is covering up the negative. Okay, -2, 0. Right here's. Let me try that again. There is -2, 0. Right. We could graph that all day long. You've been able to graph it since you were in probably 6th grade. Right. Change our background. Now, if I'm using polar coordinates, its direction is pi. Right, because pi. Zoom out a little bit. You might be able to see. I think it's just where I have split screen. It's not showing up. But pi, we know, is right here, right? And you go out 1, 2, right? So 2 pi is the same as the rectangular coordinate 2, 0. So as you work on these, you can't graph the polar coordinates, but you can graph your original point. Or you can graph your rectangular points and change the background to see if it looks like it's in the right spot for that. So if we have our others here, we're doing x equals for cosine 5 pi over 3. So 5 pi over 3. That is right here. And our coordinates at that spot are 1/2 -√3 over 2. So our x coordinate is 4 times cosine of pi over 3 is the x coordinate there. So that is just going to be 2. So 2 is my x coordinate. And then for my y coordinate, I do 4 sine of the angle 5 pi over 3, which is going to be 4 times -square root of 3 over 2. Put this over 1. I get -4√3 over 2, but the 4 and the 2 can reduce there, so -2√3 for that. So we're just using that formula, x equals r cosine theta, y equals r sine theta. And then we're just having to pull, we're pulling cosine of 5 pi over 3. That goes from the unit circle, and we just plug it in. Make sure you replace the whole thing right there. And again, let me just show you one more time over here on Desmos, that if I graph the point 2, -2 square root of 3 on the regular axis, it looks here. See how it gives you the decimal? Right here, it's just the point 2, -3.464. But if I change the background, you can see that it also is at 5 pi over 3, right? It's in the right spot. And you go out 1, 2, 3, 4. So you can check yourself with that. I don't know that these will necessarily show up on Calculator Active. They might, possibly. They don't have to be. But if they are, you could use that to check. All right. The formula will take care of itself automatically with like those negative radii, so you don't have to, like, it's weird to say the radius is -3, but the formula takes care of itself automatically. So if you just say x equals -3 cosine of 7 pi over 6, all right? 7 pi over 6 is right here. And my coordinates there are -√3 over 2, -1/2. So I will get x equals -3 times -√3 over 2, which is going to give me +3 square root of 3 over 2. That is my x-coordinate. And then for my y, I'm going to do the same thing, -3 sine of 7 pi over 6, which is going to be -3 times -1/2, which is going to be either 1.5 or 3 over 2, whichever way you want to do that, but it will be positive as well. So those are my rectangular coordinates there. If I check here, I'm going to graph 3 square root of 3 over 2 and 3 over 2. It is, on the regular rectangular plane, it is 2.598, 1.5, right? But if I change the background, it is like 7 pi over 6 is here. But are we going towards 7 pi over 6? Not with a negative radius, right? We got to go away from, which goes the opposite direction, 1, 2, 3 for that. So that would be in the right spot. Does that make sense? Okay. The other thing that you're going to have to do we're going to talk about here, you have to go from rectangular coordinates to polar coordinates. So, same idea. I've got that same picture. If I put rectangular coordinates together with polar coordinates, I get this right triangle right here. And so, if I want to know the radius, I can use Pythagorean theorem. X squared plus y squared is going to equal r squared. So, if I want to know the radius, I would just need to square root both sides of that. If you want, you can write that like you're going to get your radius is the square root of x squared plus y squared there. And that'll give me the radius every time. For the trig, I could use sine, cosine, or tangent, but both sine and cosine are going to involve the r, which is a polar coordinate, and I don't have it, right? I've got rectangular coordinates. What trig function do I need to use if I just have x and y? That one's tangent, right? So tangent of theta equals y over x. Is that new? No, we've been using that, right? Y over, when we look at the unit circle, if we want to know what tangent is there, we do y over x. So a lot of the things that you are using for polar coordinates are just facts that happen with these types of circles that we really have already talked about. So, for this, now I guess I could go the next step right here. Let's back up just a second. Which means that theta equals inverse tangent of y over x. You could use arctangent if you want. Those are just interchangeable notations there. Yeah. Yes. Oh, I thought I had a question. Okay. All right. So if I have rectangular coordinates and I want polar coordinates, so now here's the idea. I've got the point 2, 2, or -2, 2, which if we graph with the regular rectangular background, negative 2, 2, we know how I graph that one, right? If I change my background, what angle does it look like it's going to be? 3 pi over 4, and radius is not going to be a whole number, right? It's going to be close to 3, but not quite, right? So that we can use that for just like a guess, but if we look at doing the actual problem, I can do negative 2 squared plus 2 squared equals my radius squared, right? Pythagorean theorem, because this is your x. This is your y. X squared plus y squared equals the radius squared. So that is going to be 4 plus 4 equals r squared. 8 equals r squared. We will square root both sides. So our radius is the square root of 8. You may see them break this down. That is the square root of 4 times 2. The square root of 4 is 2. We cannot take the square root of 2, so we leave it alone. You might see them write it as 2 square root of 2 for that. So that is your radius. I'm probably going to be okay if you leave it at square root of 8 on something that I see there, but on like a multiple choice, they might do 2 root 2 there. Then if I want the angle, I'm going to say tangent of theta equals y, which is 2, over x, which is negative 2. So this is tangent of theta equals negative 1. And whenever you're thinking about this, it is good here for you to think about the quadrants, okay? Which quadrant is the point negative 2, 2 in? It is in the top left. It's in second quadrant. Because there are 2 places where tangent theta equals negative 1, right? But we want the one that's in the second quadrant because negative 2, 2 is going to be in the second quadrant. And here, at this point, we've got 3 pi over 4 for that. Now, really I did inverse tangent here. If you use inverse tangent, you actually technically get negative pi over 4. But think about which quadrant your answer is in. Think about the unit circle and think about which quadrant it's in. Actually, I don't even really like this. I might mark it out. Might not do that in 3rd period. Because technically, inverse tangent should just be 1st or 4th quadrant. Which you can do if you make your radius negative, but I think it's just easier to think about which quadrant we're in. In fact, it might be a good practice for us to think about the quadrants before we do any problems, right? So which quadrant is 1, negative 3 in? What? Correct. Which one is that in the numbers? 4th quadrant. Right? So keep that in mind. You need your angle to come from that 4th quadrant right there. So I've got 1 squared plus negative square root of 3 squared equals my radius squared. That's 1 plus, what do I get when I square negative square root of 3? Positive 3, right? Square roots and squares cancel each other out. Squaring a negative makes it positive. That's there. I get, a step ahead of myself. I get 4 equals r squared. So 2 is my radius. So 2 is my radius there. And then tangent of theta is going to be negative square root of 3, y coordinate, over 1. Now, there were a couple of these on the free response part of the test, and some of us were having a little trouble finding those tangent, where those values are tangent. You're thinking, where does my y over x give me that piece? I know I'm in the 4th quadrant. It's either like 11 pi over 6 or 5 pi over 3. So you can always check, like the coordinates right here are root 3 over 2, negative 1/2. Right here you got 1/2, negative root 3 over 2. I know it's one of those two. If you check to see, like if I check here at 11 pi over 6, if I do negative 1/2 divided by square root of 3 over 2, dividing fractions is easy as pie. Flip the second and multiply. I get negative 1 over the square root of 3. That is not it, right? Even if I rationalize, I'm going to get negative root 3 over 3. That one's not it, so it's not this one. It's this one, which is 5 pi over 3. Or you could call it negative pi over 3. Would be okay too. Now, there are a few problems where I wouldn't even do this. If I graph the point 0, negative 5, that's the point right here, right? On that one, if I draw myself a circle, right, what is the radius of that circle? It's 5, right? And what is the angle at that point on the circle? What? Not here. The angle. 270 in degrees. What is it in radians? 3 pi over 2. Or you could call it negative pi over 2 if you want. Either one is fine there. So when I see one where one of the coordinates is 0, I just graph it and think about it. But you could use the formulas also. They still work for that. Although you do have to be careful because like on that one, your tangent is going to be undefined. So you got to think about where tangent is undefined, which is where you get 1 over 0 there. It'll be, I think those are just easier to graph. Okay, we are not going to do this complex number stuff. We are not going to do any of the complex stuff at the end. So you guys are just going to do numbers 1 through 16 for me. So that's what we'll look at there. Okay. All of these multiple choice questions that you get back here look daunting. They're just asking you to convert either rectangular to polar or polar to rectangular. That's pretty much what they're doing there. So they're all conversions. If you have those formulas that are in those boxes. So here and here, that is what you'll use for those problems.